So we're here at the University of Manchester, and I'm with Professor Ray Burgess, who's Professor of Isotope Geochemistry, and want to learn about isotopes, radioactive dating. So to start out with, what's an isotope?
Well, the basic building blocks of atoms are protons, neutrons, and electrons, and it's the protons and neutrons that form the nuclei of atoms and also give them their mass. The chemical identity of an element is defined by its number of protons. So, for example, a carbon atom always has to have 6 protons in its nucleus. If you vary the number of neutrons, then you change the isotopic form of your element. So, for another example, for carbon again, we know that carbon has 6 protons. There are 2 stable configurations of carbon atoms, one containing 6 neutrons and another containing 7 neutrons. So if we add together the number of protons and neutrons in each of those, we end up with a carbon-12 atom and a carbon-13 atom.
And then some of these, you said those are stable. There's some that are radioactive as well. What does that mean?
Well, yes, that's right. So some isotopes will undergo spontaneous disintegration, and they do this because they've either got too few or too many neutrons in their nuclei. And they're called radioactive isotopes because they emit ionizing radiations. That includes things like alpha particles, beta particles, and gamma rays.
And what are these alpha, beta, and gamma particles?
Yeah, so they're bits of the nuclei that are broken off from the parent isotope, and so some of them are quite massive, like alpha particles are quite heavy, and beta particles, some of those are just things like electrons.
Okay. Alpha particles are what? Proton?
Yeah,
neutron?
2 protons, 2 neutrons.
Oh, okay.
So, yeah, so essentially a helium nucleus.
Oh, okay. All right. And so these isotopes that are radioactive will emit these particles. What determines how or when these isotopes decide to emit these particles?
Yes, so it's difficult to predict when they're going to break up. So we talk about them in terms of probability, and this is where the idea of the half-life comes in.
So you can't necessarily predict that particular atom will release particles, in other words, decay, but if you look at a sample as a whole, then the probability of a certain number of them being emitting these types of radiation then becomes easier to define.
That's right. So you need to, when you're dealing with a rock or a mineral, you're usually dealing with millions of atoms. So, knowing whether a particular one is going to decay on a particular timescale doesn't really matter. You're dealing with a very large number of particles.
So these radioactive isotopes then, we can't consider each one and determine whether it's going to decay, but we can consider the bulk and determine a probability then of a certain number of these decaying. What's the best way that we can measure this decay rate?
Well, the easiest way of measuring it is in terms of the half-life. And this is the time it takes for half the number of parent radioactive isotopes to decay. So let's consider an example where you have 100 atoms of a parent radioactive isotope, and you anticipate the probability that 50% of these will decay in 1 hour. So after 1 hour has elapsed, you will have 50 of the original parent atoms remaining and 50 of the daughter isotope that's formed. Then if you allow another hour to elapse after that, you'll add another 25 daughter atoms through the decay process. And we can think of this as in terms of a half-life, where the half-life is the original number of radioactive atoms that are remaining.
Okay, and so by looking then at the ratio of the daughter atoms to the number of parent atoms still remaining in the rock, we can then determine something about how old the rock is?
That's right, yes. So this forms the basis of geological age dating using radioactive isotopes. So I'll give you some examples first, perhaps. So some common ones that we use in geology are the decay of potassium-40, a radioactive isotope of potassium that decays to stable argon-40. And this occurs with a half-life of about 1.2 billion years. Another example would be the decay of rubidium-87 to strontium-87. And this has a much longer half-life of 48.8 billion years.
Wow.
So we can still use these decay processes even though they occur over extremely long timescales.
And so maybe what some people watching this may have heard of is carbon-14 dating.
Yeah.
How does that compare to those two, which have billion-year half-lives?
Well, carbon-14 is an isotope that's formed in the Earth's atmosphere, and it decays over a timescale of about 10,000 years. So it's useful for dating processes that are on the timescale of maybe 50,000 years or less. But in terms of over geological time, it's a relatively short interval.
I see. And so if we were to take a rock sample and you were to run it through your lab and determine this ratio then of parent to daughter isotopes and came up with an age of this rock is 2 billion years old, what would that represent? What exactly happened to that rock 2 billion years ago that we are dating? What does it mean?
Okay, so there are a couple of things here. Firstly, it's the sort of concept of what an age actually represents. So for some rocks, that's very easy to think about. So if you're considering a lava, for example, that could have been the point that the rock crystallized and that actually traps that moment in time. Whereas if you're thinking about a metamorphic rock, well, a metamorphic rock forms over a much longer time period, and it could take millions of years for that rock to form and cool down. So there, the age is a much more less well-defined moment in time. But essentially what you're doing is you're capturing the moment that the daughter and parent isotopes became frozen in that sample. So the point where they could no longer be lost from the sample itself.
And for sedimentary rocks, that would be the time at which those grains were formed in the parent rock, not necessarily the sediment itself.
Yes.
So you can't really use radioactive decay as a measure of when these sediments were put down.
Not so easily. If there are new minerals which are formed during the sedimentation process, then they are amenable to dating, so that can give you the age of the sediment. But you're quite right. Very often what you're measuring are the ages of the parent rocks that were eroded to form the sediments.
Okay. Well, thank you, Ray, and thank you for your time.
Okay.